All right, so we are looking at lines and planes, okay? This is Unit 8, and we're going to be looking at lines, vector, scalar, parametric form, defining a line, and we're going to stick with 2D today, all right? Our learning goal is to learn a new way of writing a line or a linear equation. This new way is a vector form, and then there's a parametric version of that vector form. The success criteria is that we convert from vector to parametric form of an equation and learn their respective parts, okay? Now, here I've got a little quote that says, a line is a straight one-dimensional figure having no thickness and extending indefinitely in both directions. That was Euclid who said that. So basically our goal is to attempt to define a series of points that successfully fit this description here, okay? So we will use three notations to represent a line in this section. The first one being scalar notation, all right? And there's a little asterisk or star here that says, note that this notation for a line only works in two-dimensional space, okay? And the reason why this one only works in two-dimensional space is because, well, let's take a look at it. It's ax plus by plus c equals 0. There's the 0 over there, actually. Now, that's a way of writing a line, right? There it is here. That line has got an x, it's got a y, and it's got a couple of numbers in it, all right? Just like we're familiar with our old way of writing a line. Remember the y equals mx plus b, where you've got an x, you've got a y, and you got a couple of numbers. This number is the slope. This number is the y-intercept here. And then you've also got this one. This is called the point slope form, where you've got y minus y1 equals m and x minus x1. Right? This is the point slope form because that's the slope, that's a number. This is an x and a y coordinate, that's just a point. And then you've got an x and a y, like you actually have the letters x and y in the formula, okay? And so here, this is our new way of writing a line. For some reason, they've decided to have a new notation called scalar notation, where they basically just pass everything over to one side, right? And you set it equal to 0. So you kind of just if you can get this into scalar notation by subtracting the mx and subtracting over the b, and you'd have basically y minus mx minus b, right? That's what you would have, okay? And so that's the scalar notation, all right? So back to this question, why doesn't this work in 2D, right? Well, why doesn't this work in 3D? I said that wrong. It says this only works in 2 dimensions. So what other dimensions are there? Well, there's a 3-dimensional scenario as well, okay? This does not work in 3 dimensions because if you attempt to write this down, or if you write this down, right, and you tell people, and then you enter a 3-dimensional space, and you bring this thing with you, something. Let's say this is like 4x. Well, here, let's take this one here. 2x plus 7y plus 5 equals 0. Let's say you bring this thing with you. This is a line, okay? And you bring it into a 3-dimensional space scenario, and you tell everybody, hey, everybody, I'm in 3D, and I've brought myself a line, and here it is. If you go and try and plot this, like, for example, like figure out all the solutions and make all the points, you try and plot this in 3-dimensional space, it will not be a line. Actually, it will be a plane, okay? And so that's why this thing doesn't work in 3-dimensional space. If you attempt to graph this in a 3-dimensional space, you will not successfully graph a line, you will graph a plane, okay? And so, therefore, this technique, this scalar notation, only works in 2D, all right? And so, that's what we got there. Okay. I wanted to mention this. You see this AB is normal to the line? Normal means perpendicular, right? And so here I've got this line. 2x plus 7y plus 5 equals 0. Here it is. Question is, why is 2, 7 perpendicular to the line? Okay. Well, first of all, I'd like to graph our line. Okay. I'm going to graph the 2x plus 7y plus 5. So I'm going to go over here. This is my 2x plus 7y equals 5. So what I'm going to do is I'm going to basically get a point on this line. Okay. So I'm going to make x equals 0. So I'm getting the y-intercept. If I make x equals 0 and I solve for y, I'm going to subtract 5 and divide by 7, and I get y equals negative 5 over 7. So therefore, on my my y-intercept, I set x equal to 0, and I determined my y-intercept is negative 5 over 7. There it is, negative 5 over 7. Okay? And now, I'm going to get 2 comma 7. 2 comma 7 is basically perpendicular to the line. Here, this vector is the 2 comma 7 vector. So notice I'm going over 2 and up about 7. See this 1, 2, 3, 4, 5, 6, 7. Remember that I'm starting at negative 5 over 7. So I'm starting at just a little bit less than 1, and I'm going up, well, actually, 1, 2, 3, 4, 5, 6, 7. So this is the vector 2, 7. And here's my line. Theoretically, these are perpendicular, okay? So this is the line 2x plus 7y plus 5 equals 0, all right? So let's actually figure out the slope of this line as well, right? Well, the slope of this line is essentially something that's perpendicular to 2, 7, all right? Well, how do so what I'm going to do is I'm going to build a vector that when I dot it with 2, 7, I'm going to get a 0. So I built this vector, 1 and y, okay? And I've left this a y, all right? And now I'm going to go ahead and perform this dot product. So 2 times 1 is 2. 7 times y is 7y. This should equal to 0. So I get y equals negative 2 over 7. I put that back into my vector, okay? This is the slope of the line. This is parallel to the line because this guy is perpendicular to the line, okay? Remember, this guy is perpendicular to that, meaning that this is now parallel to the line because this is also, 2, 7 is also perpendicular to the line, okay? And so here we have it again, just a similar scenario, right? Here's my slope, by the way. If I write it in slope form, my rise is negative 2 over 7, and my run is 1, right? My rise, because this is my y component of my vector. This is my slope vector. And this is my x component of my vector, all right? Anyway, so that was scalar notation, okay? And here's my slope, sorry. Let me just finish that thought out. Negative 2 comma 7, right? If I go, over 1 and down, over 1 and down negative 2 sevenths, I've got a vector that's basically parallel to that line, okay? So there's our scalar notation for a line. It's ax plus by plus c equals 0. What do you want to take away from that? It's AB is perpendicular to the line that you're attempting to define with this formula. Okay, so that's kind of fun. All right, now a vector notation, right? Vector notation is a new method for representing a line in 2D. Okay, and it's a vector equation, right? Note that the only way to define a line in 3D is using this vector notation, okay, and parametric, which we'll talk about in just a moment. So basically our vector notation is this, okay? Essentially what we've got here is we've got this equation right here is the actual equation of the line. So if I were to write this all out and put some numbers in place of these things, I would successfully define a line. All right. So let me explain how this works. Okay. So this is R plus RO. Sorry. This is R equals RO plus TM. All right. Well, what are these things? R is simply just this XY, right? Note that these two above equations are just the same thing written differently, right? So this is this. RO is this. T is there. And M is this vector, okay? And so basically, I'm going to explain each of these parts. What is the R vector? The R vector is a position vector that actually indicates every point on the line that we are trying to describe, okay? So it's actually the X and the Y components of a line. So remember back up here when we defined a line. Oh, I can't go up anymore. Why can't I go up? Uh-oh. I'm going to pause video. Technical difficulties. All right, figured it out. Sorry about that. Going back to here. So the question was, what is R? R is the actual vector that defines the line, okay? And it points to every position on the line, all right? So what we're going to get here is we're going to successfully define a line here, all right? You know what, I'm going to erase all this so that we can kind of see it go down, right? It kind of ends up making a little bit more sense. Give me just a moment. Flip some things around. Find my pen. There it is. All right, so we got that, and we got that. We're all set. All right, so basically, this is now an important little discussion here. Essentially, what we've got is we've got this guy, RO, and this is XY, okay? Remember up here where we actually had the line 2x plus 7y plus 5 equals 0. You need an x and a y when you define a line, right? So in our vector equation down here, our x's and our y's are sitting right there. There it is, x, y. And these guys here, this xo and this yo, that's going to end up being your numbers. And this M1 and M2, that's going to be also end up being your numbers. And then there's this T here. This T, I'll explain in just a moment. So when you write all this out, it's going to be like x, y equals like something like 3, negative 2 plus T and 4, comma 1, for example, right? So there's going to be numbers here and here. So let's talk about what these numbers are, right? Well, basically, in order to find each individual point, x and y, in order to find the x coordinate, I basically do this vector addition over here. So the vector addition would say this plus t times m, because remember, this is a vector, that's a scalar, and if I multiply a scalar into a vector, this t just goes into this and multiplies into both of these. And then I take this first component and I add it to that first component, and I end up getting a vector. Well, what vector? This vector here, okay? So basically, in order to get the x coordinate of a point on my line, I take the first components here and add them up, multiplied by t. In order to get the y component, I take the second components here, add them up, but this is multiplied by t. All right? So what is RO? RO is the starting point on the line, used as a reference to define all other points, okay? So basically, it's kind of like if I start out with some RO, let's say I've got some line and boom, I've got, here it is. This is RO. So this would be XO and over here would be YO. All right, some points. And now let's say that means basically this is some point in space, okay, over here at the end of it. All right. This RO vector is just pointing at a point. That point is a point on the line that I'm attempting to define. All right. And it happens to be known as the starting point. Why is it the starting point? Well, because this is the point where t, if you let t equal 0, right, then this whole term goes away, and RO XO is the point, is like the first point on the line here. Okay. And so that's why it's the starting point. That's when t equals 0. T oftentimes stands for time. All right. And so there you have it there. And so when time is 0, that's what you've got, a starting point. Now, let's take M. M is the slope of the line, all right? So watch the way that this unfolds. I'm basically telling, when I write some numbers here and some numbers here, I'm attempting to define a line. So let's say I end up having a 1 and a 1 here. Sorry, negative 1. That means basically my slope would be 1, negative 1. My rise would be negative 1, and my run would be 1. So I'd be like down 1 and over 1. And there would be some other point on the line, okay? This is just for the scenario 1, 1. I could have anything in this, all right? And so basically, if I now let's talk about t. T is called the parameter, and it is the value that varies. So the t actually varies. These guys stay stagnant. The XO, the YO, the M1, and the M2. The t actually varies over and over and over, and you can let it be whatever you want. So let's take a scenario where t is 1. Basically, let's figure out a point on the line. It says XO, go to XOYO, and then add to it 1 slope vector. Okay. So that's basically telling people to go here and then add to it 1 slope vector, and you end up with basically that. And that's where the t equals 1. Okay. Here, t equals 0. And there's a point on the line. What if I let t equal 2? Then if you let t equal 2, then you're basically telling people, go to XOYO and add to it 2 slope vectors. All right. Well, if I do that, I go to RO, which would be, this, and then I add to it 1, 2 slope vectors. So I end up with right there. That's where t equals 2. If I let t equal 3, then I could say, go there and add 3 slope vectors. And if you kind of look at what I'm doing here, is I'm defining a series of points that they all land on the same line. What if I let t equal a half? Then I'm actually defining that point right there. This is where t equals a half, right in there. Because basically, if I let t equal a half, it says go to the starting point and then add to it a half of a slope vector. So basically, I could define a half. I could define that point. I could define this point or that point, all by just letting t be various values, okay? You could even go back this way by letting t equal negative numbers. It says if I let t equal negative 1, then it says go here and then go backwards that direction, and you've defined a slope vector, all right? And that slope vector is where t equals 1. No, sorry, negative 1, okay? So that's what we've got there. And I could do negative a half and so forth. I could go negative 2 slope vectors. And basically, I've just defined a series of points here. What do all these points have in common? They all lie on this line. And that line is time. I don't know why I wrote time. I want to write line. That line is defined as x comma y. All of the points are x's and y's, and they can be found by going to RO, or XOYO, and adding to it the slope vector. Basically, I was just going to write this down there. All right. And basically, this is a new way of defining a line. Okay. Let's now take a look at what's called the parametric notation. Okay. The parametric notation, basically, you start out with the vector notation here, all right? Here, I'm going to start out with the vector notation, which is this one up here. So x comma y equals XOYO plus t m1 m2, right? And I'm going to ask myself, how do I get each of the x's and the y's? I'm basically going to isolate x in this equation here. Well, how do I get that x? I get that x by basically taking xo and then adding to it the m times t, right? And that'll give us my x value. And so basically the x value is xo plus m times t. And my y is yo plus m2 times t. And I'll show you that. To get the y, I take yo and I add to it m2 times t. Okay? And there we have it. That's the parametric format. And what happens is you'll see that in the parametric format, usually a line gets placed here, and then you define it. You call it like line 1 or something like that. This little line lets you know that x and y together make up a parametric equation, right? So now what we're going to do is spend a few moments doing some examples here. All right. So these examples are already done. You know what? I'm going to erase these guys a little bit so that we can have some fun seeing it unfold. All right. There we go. Get rid of some of this. All right. So basically, it says create a vector, right? Equation of a line that goes through 2, 3, and 4, -1. All right. So basically, I believe our answer is down here. And I'm going to go ahead and erase that. Okay. So basically, what I'm going to do here is I need, and then I'm going to draw a geometric interpretation of the line using points A and B. Basically, I'm going to take some moment to make a little graph. All right. Here's A, which is 1, 2, 1, 2, 3. And B is 4, -1. That's A, and that's B. All right. So I want to define a line, and that line basically is going to go like that. All right. I'll erase it for the time being, and we'll put it back a little later on. And I want to define it using a vector, this new vector style of equations. Okay. Well, a vector equation looks like this. XY equals some stuff plus t and some stuff, where this is the slope and this is some point on the line. Well, this is going to be pretty easy, actually, because check this out. I already have a point on the line. It's 2, 3. And the slope of the line, well, I can use A and B. It's basically the rise over the run. I'm going to go rising down, and I'm going to run over, right? Well, let's just remind ourselves, what's the slope formula? It's y2 minus y1 over x2 minus x1. Don't forget the slope formula. And so basically, my slope is going to be -1 minus 3 over 4 minus 2. I always mess that up, but I think I got it right. Did I get it right? I believe I did. And so this is my rise, and this is my run. And as it turns out, the run goes here, and the rise goes there, because this is the x component of the slope, and this is the y component of the slope, right? There you go. Now, don't get this mixed up with the scalar equation, which was the first one, that had something that was perpendicular to the line. No, in the vector equation, this is parallel to the line, and this is some point on the line, okay? So there it is. Now we're going to draw a geometric interpretation of the line using points A and B. Well, basically, this is RO, right? Oops, that was capital R. This is RO. Basically, this says, hey, this is a vector that tells you to point to the first point on the line. And then this says, and then T tells you to go in this direction, either far or in the negative direction, or, not so far. You can go, you could go 10, you could go 1, you could go anything. Remember, T could be anything, right? So you could have like 1,000,000 right here, and it says go 1,000,000 slope vectors from RO, and you're still going to be on the line, right? But my slope vector is this, right? Oops, that was not this proper slope vector. My slope vector is that right there. And basically, I've defined point A and point B, right? But that's where T equals 1. This is where T equals 1. Now, if I let T equal 2, then I would define another point down here, and so forth. And so basically what we say is well, let T just equal T for the time being, and we'll let the user of this equation decide what T should be. And therefore, this is now an effective technique, or an effective way of defining a line in two-dimensional space. Okay? Now remember, this is going to be the only way of defining a line in three-dimensional space. So that's something to keep in mind. Okay, don't forget that. All right. So now what we're going to do is we're going to convert the above equation into parametric and scalar forms. Okay. So basically, again, I'll start this over so we can kind of see it all happen. So the above equation is here. I'll go ahead and bring it down. So xy equals 2, 3 plus t, and it's 2 negative 4. Okay. Now, I have to convert that above this equation into a parametric. Well, first thing I'm going to do is I'm going to do the parametric. I'll do it over here. So remember, the parametric takes on this format, where you write a little line, and you call it line 1, and you define the y and the x components. So the x component, I just define it as 2 plus 2t, right? So it's just 2 plus 2t. And the y component is simply 3 plus a negative 4t, or I guess it would be 3 minus 4t. So 3 minus 4t. There is the parametric version of that line. That's easy. Now let's define the scalar equation. Remember, the scalar equation looks like this. ax plus by plus c equals 0. And we're going to need some numbers in the a position, the b, and the c. So how do we do that? Let's remember that this here is parallel to the line. All right. So now I just need something that's perpendicular to this vector. Because if I can build something that's perpendicular to this vector here, then I can get an A and a B. Because remember, A and B are predefined as being perpendicular to the line, okay? Well, I'll tell you, in order to get something that's perpendicular to this vector, I just need to create a 4, 2 vector, right? Because now if I dot these guys here, if I dot this vector and this vector, I'm going to get a 0. Because look, what's 2 times 4? 8. What's negative 4 times 2? It's negative 8. What's the sum of 8 and negative 8? 0. And so, therefore, the dot product of this and this is 0. Therefore, this and this are perpendicular. And therefore, that's the slope. This is perpendicular to the line. So, therefore, A and B are 4 and 2, respectively. So, there we go. I've got 4x plus 2y plus c equals 0. And then look at that. All I need to do is find the c vector. But remember, 2 comma 3 is a point on the line. So if I put a 2 here and a 3 there, I can solve for the c vector. So I'm going to go 4 times 2 plus 2 times 3 plus c equals 0. And if I solve for c now, I'm going to get 8 plus 5. What is that? No, that's not 5. That's 6. 2 times 3 is 6. 8 plus 6 is 16. If I pass it over that way, I get c equals negative 16. And so my equation is 4x plus 2y minus 16 equals 0. And now, I'm going to tell you, if you go and you graph this equation, which we did, then you get a line. If you graph this equation, you get the same line. And if you graph this equation, you get the same line. Spectacular. All right. Here, let's determine if C is on the line. Okay, this one's pretty simple, so I won't go ahead and go through it. Now, I'm going to start with the scalar version. So I'm going to take this scalar version. 4x plus 2y minus 16 is... wait a minute. 8 plus 6 is not 16. It's 14. Shoot. There we go. Let me change that to a 4. Silly me. There. There's our 14 right there. All right. So now if you graph this, and that, they will all be the same line. Okay. Now, question is 5, 2 on the line? Well, this is pretty easy. To use the scalar equation, all you do is you put 5 in here and 2 in there, and you see if you get 0. If you get a 0, then it's on the line. If you don't get a 0, it's not on the line. Okay, but what about the vector version of the line, which is this one up here? Well, my advice is don't use the vector version. Use the parametric instead, which is this. So I took the parametric version, I wrote it here. Okay, but instead of the x and the y, I've placed a 5 and a 2, right? Negative 2. And now the question is, I solve for t in both of these equations. So if I solve for t here, and I got 3 over 2. Solve for t here, and you get 5 over 4. Since 3 over 2 and 5 over 4 are not the same thing, basically 5, negative 2 is not on the line. That should be an on the line. All right, it's not on the line. Okay, this point 5 comma 2. The only way you know it would be on the line is if I got the same t value under both cases. Okay. Next example. What is the value of x when y equals 6? This one's pretty simple. Basically, if I use the scalar equation here, I take y and I replace it with a 6 and I solve for x. There you go, 2 over 4. What is the value of x when y equals 6? If I use the vector equation, I'm actually going to use the parametric again, okay, then what you do is you basically take this, you write it down, but you let y equal 6. So I'm going to take this and let y equal 6, and then I'm going to solve for t, and I get 3 over negative 4. Now I'm going to take that t and I'm going to put it into the x equation, and then I can solve for x, and I get a half. And sure enough, when y equals 6 here, then t equals 3 over 4. So 3 over 4 goes there, and then that gives you the x component. So basically, if I want to find what x is when y equals 6, I just take that number there, and I work my way around like that. All right. And it turns out I got the same answer in both cases, 2 over 4 and 1 over 2. They're both equal to a half. All right. Another example here is find a vector that's perpendicular to this line. Well, we already know that our line is got a slope of negative 2, 4, and 4, 2 is, I know, also perpendicular, but we have to prove this. One proof is to dot product these guys and get a 0, right? And that's our proof. So if I dot product this stuff, I get a 0. All right. Tomorrow, we'll talk about some 3D variations of this. Hopefully this video worked. There you go.